I'm actually in the Oxford University Maths Institute as I speak in the middle of a meeting, so I've just nipped out to give this talk. And unfortunately, I missed Sohan's talk, which would have been quite interesting because I did spend 5 years working on the Airlander airship project before getting involved in drones, which also originally was planning to be optionally manned. So there's lots of things I can talk about regarding that. But what we're going to talk about today is using machine learning to solve drone challenges. So just as background, the company that I'm Chief Commercial Officer of is FlareBright. We're 15 people, small company in the UK, mainly software engineers, computer scientists. We've got some kind of normal engineers, kind of mechanical aeronautical engineers, and our two co-founders, one has a PhD in autonomous systems, the other has a PhD in artificial intelligence. That sort of gives you an indication of who we are. We've had a number of funding streams from the Ministry of Defence, from the US Department of Defence, from the UK government research and technology. We've also won a number of awards, and some of those are on screen, and probably most relevant recently, we were part of Boeing Corporation's Aerospace Accelerated program for 3 months earlier this year, which they selected 10 of the world's leading AI on autonomy companies to work with them and get involved in their organization. It's a particularly brilliant program. The cohort 4, fourth year of running it, is open now. I'd highly recommend any small companies interested in that to look at that and try and get on it. It's really, really good. So that's who we are. But what do we do? So our premise is that beyond visual line of sight is critical for any useful, commercially useful drone operations in the future. And I think I've probably got a like-minded audience who will agree with that. And this schematic here talks about, well, what sort of things do you need to solve in order to allow BVLOS flight to happen? So right from the word go, before you've even taken your drone off, you need to solve regulatory problems, you need to solve assurance, you need to assure that your drone will work in all environments. And the complex development, particularly with eVTOL and transitions from horizontal to vertical flight, is going to become important. You've got complex pre-flight planning going to happen more and more. There's in-flight things. There's other things that haven't really been addressed too much, like unreliable sensors. So the sensors can break down because we tend to use these tiny little $10 MEMS chips and accelerometers, etc. And they often will break down, and they will often break down in extreme temperatures and in extreme G-forces, which easily can happen in a drone. You have varying winds, and you have some really weird wind patterns near the ground, and particularly at the right of this picture is in the urban environment where you've got skyscrapers and you get the sort of canyoning effect. And then, as you mentioned in the introduction, there's lots of GPS problems. GPS spoofing, GPS jamming, communication jamming, and with interference that will happen more and more anyway. And I think with general malfeasance and the fact it is so easy to do this, I think it will just happen naturally more and more. So those, notwithstanding through life upgrades and expenditure, these are the problems that need solving. So what do? We use machine learning solve these problems. And why? Because it's quicker. So we can run a year's worth of tests overnight. And what we do in our digital twin environment is throw every conceivable scenario we can do into a really efficient coded environment, and then we can run every wind condition, every angle of attack, every turn angle, every control surface variation, and just throw them all together, and we get a year's worth of tests really well. And we just have a very tiny amount of seed data to allow that process to happen. It's obviously cheaper. We reckon we save about 90% of money versus real world testing and versus wind tunnel testing. And finally, it's more efficient. So it allows you to a lot easier find the optimal approach. There's a lot of things in aviation that are not optimal. Even the design of passenger aircraft is not optimal. It's optimized in terms of cheapness and minimum of changes between variants. We're a long way from creating blended wing, optimal, commercially viable passenger aircraft. Machine learning overlay really allows you to hone in on the optimal solutions, optimal flight paths really quickly. So that's why we use it. So I'll give you 3 examples of how we've used this in the past. So you mentioned GPS fails. Well, this is a trace of, an obvious trace of just from a GPS running watch. And clearly, I ran 2 laps of this loop. Obviously, my GPS showed me that I did something quite different. And if you're in a critical drone environment, this is problematic in that, if you're even 5 meters out of line with where you think you are, you might be crashing into a building, particularly in an urban environment. You might be hitting the ground if you're 5 meters wrong, because they're flying a lot closer to things than other normal sort of passenger aircraft, and you don't have that visual sight. So we take an approach of looking at the whole GPS stack, or the whole navigation stack rather. So we start with GPS, and GPS, when it works, brilliant, and that's a good starting point. At some point, I think ADS-B transponders may well be sort of another solution that comes into the mix. And then what the next layer is, well, can you use vision radar terrain navigation? That's still, when the weather conditions are perfect, that works really well. But often the weather conditions aren't, and often you might be over a body of water. And I just flew from this week from Land's End, which is the bottom bit of Britain, to the Isles of Scilly, about 30 miles away. And they've done a few drone trials, BVLOS trials. You cannot notice which bit of water you're on there. That's impossible. So what we use is this machine learning navigation. And so we've effectively created an inertial navigation system that then allows you to have another layer of assurance and another layer of safety to kick in. And it also measures when all of these systems are working, when they're not working. So that's our approach, is to say we need a multi-layered approach to navigation in drones. And our inertial navigation system, which just uses the normal sensors in a drone, is part of that layer. It's not a unique solution on its own, or it can be for short periods, but it's really part of a layered approach. And how we've done that, so we started off just on a drone that we created ourselves with a box wing, and we've got with 30 seconds of totally autonomous flight on a predetermined program, basically taking, in a very simple terms, and it's more complex than this, but if you think of an accelerometer, the tiny accelerometers that tell you which way up your phone is, those same accelerometers, put them in an XYZ array, and every time you feel a force, that force is the wind, and you can react against that, and then you will know what your position is. So our machine, our flight control system, has trained our drone to know that. We thought, great, that works really well. So let's put that in just a hobbyist drone. So we used an Opteron fixed wing powered, electrically powered hobbyist drones with polystyrene wings, and we ripped out their flight control system. We put in our flight control system, and we've done exactly the same. And we fly circuits and spirals and everything autonomously on predetermined flight paths to a high degree of accuracy using our techniques. And then what we'll eventually do, and we're being funded by the US government and the UK government to do this now, is to put that same system in as many other drones as we want. And it takes us a few months to model all the characteristics of another drone in order to achieve that. And what we've done, and what differs ourselves from pretty much every university project that's tried to look at machine learning systems, is normally the error rate runs away exponentially really quickly. And because we've got this machine learning overlay that models and caps the error, we've managed to create a linear growth rate of error. So we do get an error, but it grows linearly. So we know exactly what it should be at any particular point of time. And that's really important. So that's what we're doing on our inertial navigation system that's got lots of uses in both the defence sector and in the civil sector, and particularly the BEAD. But if we come back, and I gave a very simple idea of saying we have accelerometers and XYZ array. Well, actually, what we do is we take every single bit of data we can. And it's like, and this is why I put this Sherlock Holmes detective character. We kind of think of the machine learning like a detective who every sensor on board any drone is giving away some information, some clue as to what that drone's doing. You know, the temperature is giving some information, the gyroscopes, the magnetometer, the barometers are giving some information. And it's about harnessing that huge data set of information to understand what's going on in order to use that. And most of this data is only used for single use. It's used for maybe understanding how the engine is functioning, or it's just thrown away as junk data. It's not really involved in the flight control systems. And that's what we use. And even things like current voltage, we do all of this on a Raspberry Pi Zero when it's in flight. So we use the machine learning and train everything offline using pretty much standard reinforced learning technique. And then we go back online onto something as small as a Raspberry Pi Zero, and we control the whole drone autonomously on predetermined flight paths using that. And I think this wasted data is an area that we're really looking at. And these are some actual data from us. When we use all the telemetry from our drones, it really reduces error. So our flight test verified system brings our error rate on the first graph there right down over 30 seconds. So from a normal inertial navigation system based on sensor data, the nav error runs away really quickly, the navigation error, and we cap it because we're using all the data, because we've got this machine learning approach. And then ditto on this other graph, what we've got is actual flight data and you can see how it's still oscillating quite a lot around what we're actually trying to do in terms of the attitude and the speed over time. But we're pretty much tracking exactly what flight plan that we've gone in, which is the kind of dotted square blocks. We're oscillating around it, and as we improve the machine learning, as the machine learning runs over time, it gets closer and closer to the actual answer. And finally, if we look at 3D unsteady wind patterns, we did a really interesting project which is ongoing, has been funded into phase 3 with the UK government, and we've just presented the findings of this project at the International Council of Aeronautical Studies annual conference in Stockholm, about modeling the wind in an urban environment in 3D. And we think that's going to be critical to allow smaller drones to fly in urban environments, whether it's drone delivery or any sort of emergency service kind of monitoring surveillance. And the drones really struggle in gusty environments, and they really struggle understanding round, and this is central London, but you know, the winds around one side of the skyscraper are going to be very different to the winds around the other side. So we did a project at Cardiff International Airport where we worked with a computational fluid dynamic modeling company called Xenotech, and we were looking at the wind vortices coming off this massive British Airways maintenance hangar. So you can just see the people in yellow high-vis vests. That's our team, with a windsock and an anemometer just to measure what's going on at about 3-4 meters. And our drone flies, and because it understands where it should be, and it's react against the wind to stay on that same flight path, you can back solve that to measure exactly what the wind is. And again, that's a function of our machine learning approach offline. We know exactly what the wind is to a really high degree of accuracy at all times. And as I said, we can put this in any other drone. So as you're flying, you will know what your wind is without a pitot tube, without anything else, just from the sensors in your drone. And as you can see in the top diagram in the middle, we're absolutely seeing crystal clear where the vortices rotate and the wind comes from the other direction. And then when the wind's blowing towards the hangar, as it was on a different day, we get this really smooth airflow in the bottom. But what's even interesting there, at the very bottom, we can see a little bit of wind shear, and that was between 3 meters and 4 meters. We're getting that level of granularity just with bits of ground effect and sort of wind coming off some of the fins of the large aircraft that were waiting to go into the maintenance depot. So that's just an interesting kind of side effect of what we're doing. And where our machine learning ecosystem is going with this is looking at mission optimization, in-flight failure monitoring, especially GPS spoofing and denial, degradation of sensors, degradation of performance, rapid development. We're getting heavily involved in GPS-free navigation, both for BBLOS and for military and for wind sensing, as I mentioned. So that's us really. Hopefully that's a quick whistle-top tour about how we're using machine learning, digital twinning to solve real-world BBLOS drone problems. And I'm happy to take questions for a few minutes.